Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is the fourth video, at least I think it is. Yeah, this is the fourth video in a series on solving trig equations. The first one was all about the concepts behind solving trig equations, and I had some good advice in there. And the second was solving basic trig equations. The third was solving trig equations requiring the use of identities. And we're in this last one, well, actually second to last. The last one's actually using technology, but this one right here is solving multiple angle equations. And these are equations that have, well, multiple angles. And we've already sort of seen how to do this, but I definitely want to go ahead and spend a video going through and showcasing this because it is a very nice, easy technique to use. Just the problem is you kind of sometimes have to check your work. So let's showcase how that's done here. Let's find all solutions to this equation. Well, we have something squared is equal to 3/4. I'll take the square root of both sides. Just to let you know, when you take the square root of both sides, you do not have, that does not force you to check your work in the end. You can actually just take the square root of both sides and it will not destroy solutions. So you're okay by doing that. Just remember, you get a plus or minus. Square root of 3/2. And then you just reference your triangles. Where is it? I just pasted it in here. There it is. So you reference your triangle there. And let's see, the sine of what angle gives me √3/2? Oh, that'd be the sine of pi/3. So I know my reference angle is pi/3. But what is my angle? The angle is not theta, it's actually 2 theta. So when I say reference angle, I really mean 2 theta hat. That's the reference angle, and we want that to be pi/3. Now you ask yourself, where is the function, the sign, positive, and where is the sign negative? Well, that's all 4 quadrants, right? Quadrants 1 and 2 is where it's positive, and 3 and 4 is where it's negative. So it really is almost the same stuff we have been doing. Quadrants 1, 2, 3, and then 4. We have a reference angle of pi/3 in quadrant 1, means our angle, which is 2 theta, not theta, but 2 theta, is pi/3. Do we want all solutions? Yeah, we want all solutions. So I'll say plus 2 pi k. Again, in quadrant 2, our angle, which is still 2 theta, but with a reference angle of pi/3 is 2 pi/3. And then plus 2 pi k. In quadrant 3, our angle, 2 theta, is equal to, let's see, we have a reference angle of pi/3 in quadrant 3, that'd be 4 pi/3, and again, plus 2 pi k. And finally, in quadrant 4, our angle, 2 theta, is equal to 5 pi/3, because that has the reference angle of pi/3 in quadrant 4, plus 2 pi k. Now, take each of those equations, divide by 2, so that you can find out what theta is. So each of those equations, just do a simple division. You get theta is equal to pi/6 plus pi k. You divide everything by 2, not just the first term, but everything by 2. That's how mathematics works. Second equation, theta is equal to pi/3 plus pi k. Third equation, theta equals was it 2 pi/3? Yeah. Plus pi k. And last equation, theta equals 5 pi/6 plus pi k. All right, so those are all the solutions. That's actually all solutions to this trig equation. You may say, well, then it's not really that different than what we've been doing. And it isn't. It actually isn't that different, except for one little thing. Let's suppose that I had said I need not all solutions, but only the solutions between 0 and 2 pi. Well, if I wanted the solutions on 0 to 2 pi, in the past, what we would do is we'd let k equal 0, and we'd be done. So if you let k equal 0, you get pi over 6, pi over 3, 2 pi over 3, and on the last one, 5 pi over 6, right? But because our angle is going twice as fast, that's what sine of 2 theta is, it's an angle going twice as fast, it actually carves out the sine twice in that 0 to 2 pi period. So just double check. If you let k equal 1 here, you'd have pi over 6 plus pi, which is 7 pi over 6, which is still between 0 and 2 pi. If you went to the next equation and let k equal 1, you'd have pi over 3 plus pi, and that would be 4 pi over 3, which is not in that list, so I'd have 4 pi over 3. If you go to the next equation and let k equal 1, you'd have 2 pi over 3 plus pi, which is 5 pi over 3. And again, last equation, if you let k equal 1, you have 5 pi over 6 plus pi, which is 11 pi over 6, which is still within that interval. So notice, when I had sine of 2 theta, I got double the set of solutions from 0 to 2 pi. That's just how it works. Well, most of the time. There are some exceptions to that rule. One of the exceptions is if your ratio is if your ratio is a quadrantal ratio. In other words, if it lands on an axis. So sine of theta equals 0, 1, or negative 1. And we will likely see that, so don't worry about that. All right, so let's see what else we can do here. Find all solutions to this equation. Now, this is actually that exact situation I was just mentioning, where you have a value of negative 1 here. That's going to give us a quadrantal angle. Notice we're not dealing with sine, cosine, or tangent, but you can actually force it to be that way because we have the secant of 3x. That's 1 over the cosine of 3x, and I prefer to work with the cosine. So I'll take the reciprocal of both sides. Well, the reciprocal of negative 1 is still negative 1. So this is actually much easier for me to work with, cosine that is. And I just want to know, normally, when is the cosine equal to a negative 1? And we could see that normally it's equal to a negative 1 at pi, and then any rotation of 2 pi thereafter. So our angle, which is not x, it's actually 3x, our angle must equal pi plus any rotation of 2 pi thereafter. Well, if you divide both sides by 3, you'll get that the angle is pi over 3 plus 2 pi over 3. Okay, and we are done, literally, that quickly. There's nothing else you have to do. If I had asked, or if you have an instructor or a problem in a homework or an exam that asks you to only find the solutions between 0 and 2 pi, on 0 to 2 pi, I'll start with k equals 0. That would give us pi over 3. Then I'll graduate to k equals 1. So 0, and then I'll go to 1. If you let k equal 1, you have pi over 3 plus 2 pi over 3, which is 3 pi over 3, or pi. Then if you let k equal 2, you have pi over 3 plus 4 pi over 3, which is 5 pi over 3. If you tried to go to k equals 3, you would have pi over 3 plus 2 pi, and that's outside of this interval. So again, we had a cosine of 3x, we had 3 times the number of solutions that we were expecting. And to find them, I just let k equal 0, 1, and 2. I actually used 3 values of k. It just started at 0. So 0, 1, and 2. Those 3 values of k right there, but it started at 0, ends at 2. That observation is very, very important when you get to a problem like this. So we're going to find all solutions first, and then I'm going to say find all solutions only between 0 and 2 pi. Well, let's see. I have a sine of an angle equals a -1 over root 2. Now, that's the first time I've actually in a while done this triangle. This is the pi over 4 right angle. I just have a habit of not picking this triangle for some weird reason. But we know the reference angle, not for theta, but for tan theta, is pi over 4, because the sine of pi over 4 is a positive 1 over root 2. Now, sine is negative in quadrants 3 and 4. So let's go ahead and write out the quadrant 3 solution set. Quadrant 3, our angle, which is tan theta, well, we have a reference angle of pi over 4 in quadrant 3. That's 5 pi over 4. And then, of course, plus 2 pi k. That's all the solutions. Of course, at this point, I could actually divide both sides by 10 if I want to, so I will. Theta is equal to, let's see, 5 pi over 4. That's pi over 8. Plus pi over 5. Okay, let me double check that. Yep, that's right. And then in quadrant 4, our angle, which is tan theta, we have a reference angle of pi over 4 in quadrant 4, so that's 7 pi over 4 plus 2 pi k. Again, dividing both sides by 10, you would get theta is equal to 7 pi over 40 plus pi over 5 k. This actually is pretty obvious that it's pretty obvious I need to mention something here. Notice that initially, quadrant 3, definitely 5 pi over 4 is in quadrant 3. And any rotation of 2 pi thereafter lands in quadrant 3. But when you divide by 10, this is no longer pi over 8, it's definitely not in quadrant 3. So when I say our quadrant 3 solution, I'm really saying tan theta lands in quadrant 3. The actual answer, theta itself, might not be a quadrant 3 angle, and in fact is not. Same thing here. In quadrant 4, tan theta is 7 pi over 4, but theta itself doesn't need to be in quadrant 4, and in fact, it's not. 7 pi over 40, that's a quadrant 1 angle. All right, now suppose, by the way, these are the solutions we're done if we were asked to find all solutions. But suppose that we're asked to find only the solutions between 0 and 2 pi. Now, this would be a terribly mean question if I didn't give you a trick. The trick is as follows. On 0 to 2 pi, theta is equal to, well, okay, I'm going to show you what it would be like if I was cruel. You would start with k equals 0, and you plug that in and you say, oh, okay, pi over 8. And then you move to k equals 1, and you say, okay, pi over 8 plus pi over 5, so that's 13 pi over 40. And then you'd go to k equals 2, and so on and so forth, right? But there's a bunch of fractional arithmetic, and it's just terrible. And where do you think we would end? Remember, we need 10 of them. We start at 0. You're going to end at 9. So here's how I highly recommend you writing it. Theta equals pi over 8 plus pi over 5k for k equals 0, 1, ... 9. That gives you all 10 solutions there, and theta is equal to 7 pi over 40 plus pi over 5k, and again for k equals 0, 1, ... all the way to 9. There's 10 digits here, 10 numbers that I've listed out, so we get all 10 representations between 0 and 2 pi for that solution, but it's just better than having to do the fractional arithmetic forever, basically. So this would be the solution set on 0 to 2 pi. And I highly recommend you use that notation because it's much easier. All right. So it looked like it was going to be terrible, actually, if we wanted to actually write them out, but don't. Here's a similar problem. And in fact, we've done something like this, but might as well just do it here. Tangent of x over 2 is equal to 1. Just because it's an x over 2 does not mean you need to grab a half angle identity. You know the tangent's equal to 1. Tangent of some angle is equal to 1. That is actually a special triangle angle. It's one of the rare ones, but still, it's pi over 4, right? Pi over 4. Tangent of pi over 4 is 1. 1 root 2, right? So I know that the reference angle is pi over 4. And then I just consider what quadrants is tangent positive in. Well, tangent is positive in quadrant 1 and quadrant 3. Now, the interesting thing about tangent is it's pi periodic. And so often when dealing with tangents, you can compress their solutions down into a single solution. You're going to see that here. So quadrant 1, our solution would be, well, our angle is not x, it's x over 2. We have a reference angle of pi over 4. And then we're in quadrant 1. Now, I'm not going to say plus 2 pi k because tangent is pi periodic. So I don't need to say plus 2 pi k. It's just plus pi k because every pi, it ends up repeating itself. And in fact, if I wrote out the quadrant 3 solution, I would get that x over 2 is a reference angle of pi over 4 in quadrant 3 is 5 pi over 4. And then plus pi k. But guess what? That's actually when k is equal to 1 here. So this is repeated. It's a redundant solution. Tangent's the only one that works this way. So with the tangent, you can just compress it down to your quadrant 1 solution. Because again, when k is equal to 1, we get pi plus pi over 4, which is 5 pi over 4. So we get all of the solutions that our quadrant 3 solution would give us. And solving this for x, multiplying both sides by 2, we'd get x is equal to pi over 2 plus 2 pi k. Now, that is all the solutions. If I said I wanted the solutions between 0 and 2 pi, I would start with 0. So when k is 0, you get pi over 2. And when k is 1, well, we're beyond 2 pi. So that's the only solution. And you would have seen that as well if you multiplied this by 2. You would get the same, you'd have the same issue. I shouldn't say issue, but whatever. Anyway, but the main thing about that tangent is whatever quadrant your solution is in, pi later, you'll have that same solution. So because it repeats every pi, maybe I should say it this way. Let's suppose this was -1. Well, tangents would be negative in quadrants 2 and 4. Well, if I had a reference angle of pi over 4 in quadrant 2, it's 3 pi over 4 is the actual angle. If I have a reference angle of pi over 4 in quadrant 4, then 7 pi over 4 is the angle. These are just pi off from one another though. And so my actual solution would have been x over 2 is equal to 3 pi over 4 plus pi k, and it covers all my bases. So again, tangent, you don't actually need to list out both quadrants. Or you could, you'll just find out that you're doing double the work. So there's no real reason to do that. Now this is a good looking problem. Find all radian solutions to the equation and then state the solutions on the interval from 0 to 2 pi. Notice that's just it's a mess basically. I'm going to move all my trig functions to one side. So I have 2 cosine of 2x, sine of x, minus 2 sine of 2x cosine of x. And I'll move the root 3 to the other side, so minus root 3. Now, if you notice, this looks like a special formula that we know, sum of angles formula. I just need to divide both sides by 2. And if I do that, I'll get on the right-hand side a negative root 3 over 2. On the left-hand side, all these coefficients of 2 disappear. Now, I'm going to write this slightly differently. I'm going to write it as sine of x cosine of 2x, and then minus sine of 2x cosine of x. The only reason why I write it that way is because that's the way my brain sees this. This is the sine of x minus 2x. This picture right here is the sine of the first angle minus, because sine keeps it sine, the second angle. Sine of x minus 2x is what that compresses down to. And again, the right-hand side is a negative root 3 over 2. So we have the sine of negative x is a negative square root of 3 over 2. So noticing trig identities, very powerful. Another thing is super powerful is to note sine is an odd function. So sine of negative x is negative sine of x. Negative root 3 over 2, and you can multiply both sides by a negative 1. And now it's a really nice problem. We want our solutions in radians, so let's go ahead and just mention, I'll paste in here, wherever it went, I don't know where it is. Oh, there it is. Paste it in there, the special triangle. And we see that the sine of pi over 3 is root 3 over 2. So our reference angle is pi over 3. And our quadrants are 1 and 2. Therefore, our solutions are pi over 3 plus 2 pi k and 2 pi over 3 plus 2 pi k. And on, those are all solutions, on 0 to 2 pi, our solutions are just going to be the pi over 3 and the 2 pi over 3. So this is a really good example of showcasing that you should keep your eyes open for any type of trig identity. Sum and difference of angles identities do occur, not all the time, but when they do, it should jump out at you. If you have a sine cos and a sine cos, or a cos cos sine sine, those are the sum and difference identities for the sine. And the cosine, just be very aware that they can be thrown at you like that. They do happen. The final example in this video is to find all solutions to this equation. And this is not a big fanfare or fireworks way to end out this video. It turns out that this is not too bad, but you do need to be able to see how to do it. I have a sine of 3x minus sine of 6x is equal to 0. These are the same trig function, but totally different arguments. And so we can't combine them. We can't really do anything right now as written. I would like them to have the same angle. And it's actually easier to reduce an argument, the angle of an argument, than it is to increase its angle. So it's easier to reduce that 6x down to a 3x rather than that 3x up to a 6x. So how do we do that? Well, you can use what's called the double angle identity. You should note sine of 6x is the same thing as sine of twice 3x. So at this point, notice I'm constantly using identities in really weird, vague ways, but you have to be proficient enough with the trig identities to notice them and move into them very quickly. Because when it comes time for calculus, not in your trig course, obviously, but when you enter into a calculus class, nobody's going to remind you or say, oh yeah, this problem, when you guys do this homework problem, remember the double angle formula is, it's just, you're working on something and trig identities happen all over the place and you just have to be proficient enough to see them and do them. So the sine of a double angle is twice the sine of the angle times the cosine of the angle. That's our double angle identity. Now, if you look at this equation, both of those terms have a sine of 3x in common, so I will factor them out. And I'm left with 1 minus 2 cosine of 3x. A little bit of algebra there. We have the product of two functions equaling 0. That implies that either the first function is 0 or the second function is 0. So that means that the cosine of 3x is 1/2. And now we'll just start solving. When a sine or a cosine is equal to 0 plus or minus 1, I just draw out that trig function. Not the sine of 3x, just a sine of x. And you could see sine becomes 0 at 0, pi, and 2 pi. I should probably make sure that I'm working in radians. I'm going to, because they didn't tell me one way or the other. So I can see that my solutions are going to be any multiple of pi, any integer multiple of pi. So 3x is going to be pi k. If k were 0, I'd get 0. If k were 1, I'd get pi. If k were 2, I'd get 2, and so on and so forth. And that implies x is equal to pi over 3 k. That's one set of solutions. I didn't square both sides or anything like that, so I don't need to use, I don't need to check my work. Now we're going to deal with the cosine of 3x. I'll paste in my triangle there. And cosine of 3x equaling 1/2, well, that means that our 3x must have a reference angle of pi over 3. So the reference angle for 3x is a pi over 3. And we're in quadrants because cosine is positive, 1 and 4. Well, in quadrant 1, 3x will therefore equal pi over 3 plus 2 pi k. And I'll go ahead and just divide both sides by 3. So x is equal to pi over 9 plus 2 pi over 3 k. Our quadrant 4 solution, 3x would be, now you are actually welcome to write negative pi over 3 plus 2 pi k. That's perfectly fine. I want to give you a little heads up though. If you do that, and then if somebody asks you, what are the solutions between 0 and 2 pi, that's going to screw you up. So it's okay if they're asking for all solutions to just say, oh, negative pi over 3 plus 2 pi k. But if you're asked for solutions between 0 and 2 pi, it's probably safer for you to say, okay, I'm in quadrant 4 with a reference angle of pi over 3. That's 5 pi over 3. It's a little bit safer. But all solutions, you're fine. So divide both sides by 3 and you get x is equal to 5 pi over 9 plus 2 pi over 3k. And these are our second sets of solutions. There you go. So we have actually gone through pretty much all solution methods for trig equations. The next video, which is the wrap up, will be dedicated to using technology, which we've actually already done a couple times, but I'd just like a video dedicated to it.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.